Welcome to Missing the Mark, where we look for meaning in strange places. I'm Christopher. Today we're going to be looking at falsificationism, the idea that what makes a theory scientific is that it is falsifiable. Actually, mostly it's going to be my friend Eve Keneinan doing the talking once again, because she wrote an excellent article about the rise and fall of falsificationism within the philosophy of science, and I really want to share it. Like last time I read one of her blog posts, I'm going to be leaving the first-person singular pronouns intact, and I'll be adding some commentary, too. Also, there's a little bit of leading and trailing context which I'm omitting. I'll include a link in the description so you can read the full article, of course. What is falsificationism? It is a specific answer to a specific philosophical question given by a specific philosopher to solve a specific problem. And it failed at that, leaving in its wake a sometimes useful methodological tool and more than a few popular misconceptions. The philosopher in question is Sir Karl Popper, and the problem he was trying to solve was known in his day as the demarcation criterion problem. At the time, it was taken for granted that some knowledge is scientific and some knowledge is not scientific, that some human disciplines of inquiry are sciences and some are not. So the question arose by what criterion one can demarcate a real or genuine science from a non-science, or more urgently, a pseudoscience, claiming to be a science. In other words, how do you tell science from what isn't science? Popper's thinking was informed by the intellectual milieu of the fin des siècles Vienna, in which many exciting intellectual revolutions were underway simultaneously. Einstein was threatening to shake the heretofore seemingly unshakable foundations of Newtonian physics. Mathematics seemed, as per Hilbert's famous speech, about to be completed, before Gödel put an end to that idea once and for all. Freudians claimed to have discovered the key to the depths of the human psyche, and Marxists to have unlocked the inner mechanisms of human history. It was a heady time, in which people were not afraid to make bold, often reckless, claims. At the time, the universally accepted answer to the demarcation problem was verificationism. Something would count as scientific knowledge if its claims could be empirically verified, and the more verifications, the more scientifically sound the view was supposed to be. This theory is very easy to understand and has a direct appeal to common sense. If a theory keeps being proven correct, it is probably a correct theory, right? Unfortunately, Popper noticed something which today we would call confirmation bias. He noticed it particularly among the Marxists and the Freudians, both groups of which insisted that their respective disciplines of dialectical materialism and psychoanalysis were indeed sciences. He noted it personally in his friend Alfred Adler, the Freudian heretic who had discovered, contra Freud, that sexual repression was not the key to the human psyche, but the inferiority complex instead. What Popper noticed is that when a Marxist or a Freudian attempted to give a scientific account of a historical event in terms of class conflict, or a psychological phenomenon in terms of sexual repression and neurosis, they were able to do this no matter what the circumstances were. A Marxist could, and did, explain anything and everything by means of class conflict. A Freudian could, and did, explain anything and everything by means of sexual repression and neurosis. And each explanation which was given was considered by each as a verification of either Marxism or Freudianism, thus further proving each theory correct and scientific. Nor could one criticize Marxism or Freudianism. It was obvious that the critic of Marxism was a bourgeois apologist, which proved Marxism's class conflict theory, and the critic of Freudianism was sublimating his sexual repression into a neurotic attack on Freudianism, which proved Freudianism. As you can imagine, when a Marxist got into a head-to-head argument with a Freudian, it was like a perpetual motion machine of pointless back and forth. Popper regularly dined with his friend Adler, with whom he often quarreled about this issue. One time, Popper discovered a psychological case that seemed clear to him could not be explained by means of Adler's go-to explanation for everything, the inferiority complex, which had the same self-confirming structure as the Freudianism from which it sprang. For example, a man sees a drowning child. If he fails to jump in the water to save her, it was due to his feelings of inferiority. If he does jump in to save her, he was overcompensating due to his feelings of inferiority, and so forth. Popper waited for his moment and sprang his example case on Adler, hoping to baffle him. Instead, to his astonishment, Adler immediately analyzed the case in terms of an inferiority complex. Popper managed to sputter, "But how do you know this?" To which Adler replied, in a magisterial tone, "Based on my 1,000-fold experience." To which Popper, having recovered, replied, "And I suppose now your experience is 1,001-fold." So, the scene is half set. We need one more piece of the puzzle. Einstein's theory of special relativity was being hotly debated by physicists. Some were intrigued by it, some thought it was complete lunacy. As it happened, an eclipse of the sun was due to happen on a certain day, which would allow something not usually possible: the direct observation of the planet Mercury. Mercury is usually overwhelmed by the sun's radiance and cannot be directly observed. Einstein's theory predicts that light will be affected by sufficiently massive bodies, such as the sun, whereas Newton's theory does not. That is, according to Einstein, light should bend around the sun due to its mass. This allowed a very interesting test case. Since we cannot normally see Mercury, we do not know exactly where it is, or more accurately, where it appears to be. But at the time of the eclipse, it would be possible to look and see exactly where Mercury appears to be. In essence, Einstein's theory predicted Mercury would be at point E, due to the gravitational bending of light, and Newton's theory predicted Mercury would be seen at point N. All that was needed was to wait for an eclipse and see whether Mercury was at E or N. And as I suppose you all know, the eclipse came, and Mercury was observed to be at point E, just as Einstein had predicted, and the relativistic revolution began in earnest. What impressed Popper so much about this was that Einstein was willing to go out on a limb, so to speak, and make a prediction, which, if it didn't pan out, would have significantly undermined the credibility of his theory, but at the same time, if it did pan out, as it did, would significantly boost the credibility of his theory. In other words, Einstein was willing to make a prediction which, if it failed to hold, would falsify his theory. Marxists and Freudians and Adlerians were not willing to make predictions which would, if they failed to happen, cause them to abandon their theories. Nothing can make a convinced Marxist or Freudian abandon his or her theory. So Popper hit on the idea of reversing the demarcation criterion. Instead of verification, he argued, truly scientific reasoning risks falsification. It makes conjectures and risks refutations. A theory that cannot, under any circumstances, be falsified is not, according to Popper, a scientific theory. Thus was born the idea of falsificationism, namely the idea that what makes a discipline scientific is its willingness to risk being refuted by making risky predictions. As with verificationism, there's a kind of common sense appeal to falsificationism. It is not a worthless idea, but in any event it can't do the work Popper hoped it could, and it certainly can't do the work that Popper candidly admit that it could not, namely serve as a criterion for all legitimate knowledge as such. Hey, breaking in for a second. At this point I'm clipping out a little bit where Eve carefully shows that falsificationism fails the very test it proposes if you try to use it as a universal principle of knowledge. As she says, verificationism can't be verified, and falsificationism can't be falsified. Which is not a problem if you're only trying to use them to separate science from pseudoscience, and most people realize that there's a great deal more to real life than just science and pseudoscience. The ones who don't are probably beyond help anyway. Back to Eve. And neither principle succeeds in its more limited purpose of demarcating scientific knowledge from non-scientific knowledge either. To give the game away, most philosophers today are content to say that scientific knowledge is a Wittgensteinian family resemblance concept, and do not think there even is anything specific that exactly demarcates science from non-science. Verificationism fails for the reasons that so upset Popper. Countless pseudo-verifications can be generated almost at will for any theory. This is why Popper wanted falsificationism to be clear, cut, and dried. If this prediction doesn't happen, then the theory is falsified and should be abandoned. Why doesn't this work for science, at least? Didn't it do a good job distinguishing Einstein's theories from Marx's or Freud's? Yes. In that interesting and unusual case, it did. But unfortunately, that isn't how science actually works nearly all the time. Since the Einstein example that so impressed Popper involved planets, let's talk about those. Consider the planet Uranus. When you look for it in the night sky, it isn't where it's supposed to be, according to Newton's theory. Bam! Clear, cut, and dried. Remember, Newtonian physics is falsified. Stop using it right now. It's wrong. No, really, quit it. Except, that's not how things played out. Newtonian physics was too damned useful to throw out as Popper demanded. Instead of regarding Newtonian physics as falsified by Uranus not being where it should be according to the theory, the scientists decided that there was probably some other factor, X, which was causing the correct theory to not match up with the would-be falsifying observation. What could it be? Well, if there were another planet out beyond Uranus of this mass right about here, that would explain Uranus not being where it's supposed to be, according to the theory. Lo and behold, telescopes were pointed and Neptune was discovered. Far from being a falsification of Newtonian physics, the failed prediction of the location of Uranus led to the discovery of Neptune, which was then regarded as a stupendous confirmation of Newtonian physics. Well, except for one little problem. Now that we know about Neptune, it turns out that it keeps not being where Newton's theory says it should be. So, once again, Newtonian physics is falsified, right? We abandoned it. No. Once again, scientists did what scientists actually do, and not what Karl Popper would later say that they should do, and they decided that the mismatch between the theory and the observation was due not to a defect in either one, but due to some unknown complicating factor X. What could it be? Well, if there were yet another planet beyond Neptune of this mass right about here, and so we discovered Pluto. And another crucial scientific discovery was made due to the fortunate fact that Popper hadn't written yet, and no scientist in his right mind considered Newton falsified. Hey, me breaking in again. The history of Pluto's discovery is actually more complicated than this. The hypothetical planet X they were looking for had a mass roughly 7 times that of the Earth. When Pluto was discovered, they calculated its mass as about equal to that of the Earth. Our most recent estimates put it at about 0.2% the mass of the Earth, which, as you might guess, didn't explain the error in predicting Neptune's orbit. Eventually, it turned out that the error in Neptune's orbit wasn't due to Pluto, but due to an error in estimating the mass of Neptune. When Voyager 2 flew by in 1989, our estimate of Neptune's mass was reduced by 0.5%, which, given its enormous size, is roughly the mass of Mars, and the error in its orbit vanished, and with it the need for Planet X. Pluto, it turned out, had been discovered entirely by accident. Back to Eve. Now, it had been known for a long time that Mercury also doesn't do what it should do, according to Newton's theory. And once again, scientists hypothesized that neither the theory nor the observations were wrong, but that there was a complicating factor X, which was the cause of the discrepancy. If there were another planet here of this mass, well, it's too close to the Sun to actually see yet, but let's assume it's there. They even named it Vulcan, the planet closer to the Sun than Mercury, which disturbs Mercury's orbit. Alas for planet Vulcan, sorry Mr. Spock, we mourn for thee. It turns out that in this case the theory was wrong. Newton wasn't right, and Einstein's theory explains perfectly well why Mercury moves as it does without the need to postulate a planet Vulcan. But I hope you see the problem already from the examples given. Assume there is a mismatch between a theoretical prediction and an empirical observation. Then one of the following is true. 1. The theory is wrong or falsified. Or 2. The observation is erroneous in some way. Or 3. Neither the theory nor the observation are erroneous, but there is an unknown factor X causing the discrepancy. In brief, the problem with Popper's theory is that it requires us to know in advance that 2 and 3 can be safely ruled out. Now, sometimes 2 can be ruled out to a high degree of probability, sometimes not. But 3 is the real sticking point. 3 can never be ruled out as a possibility since, by definition, it is an unknown factor X. It is simply not possible to say, I know with certainty that there is not something I do not know about interfering in this case. This alone would be enough to sink Popper's falsificationism as a comprehensive theory of scientific knowledge, let alone all knowledge, which it never was nor could have been, but matters get even worse for falsificationism. Again, I'm not going to give you the detailed philosophical arguments behind all this, but 2 philosophers advanced very similar ideas, one earlier and one better, but similar to the extent that the general view is known as the Quine-Duhem thesis, or the Duhem-Quine thesis, whichever sounds better to you, I guess. I like the first one, even though Duhem was before Quine in making the case. Basically, the Quine-Duhem thesis states that it is impossible to test any scientific idea or theory or hypothesis in isolation, because any possible test one can devise already requires implicit and explicit embedded background assumptions. In something like Quine's terminology, knowledge, including scientific knowledge, forms a holistic system or web of beliefs and assumptions, and there is simply no way to ask, in isolation of the system as a whole, whether one particular belief or idea is true or not. It's a kind of Einsteinian relativity applied to epistemology. What Quine argued, in effect, is that one can, with rational consistency, continue to hold any belief whatever, so long as one is willing to sufficiently adjust one's entire conceptual web. At this point, Eve gives some examples which are pertinent to the context she was writing for, but since they're not scientific examples, I'm going to give a different example instead. Consider Newton's law of gravitation, which implies that the speed at which objects fall is independent of their mass or horizontal velocity. Well, the first thing to note is that not everything falls when you let go of it. Hot air balloons, for example, rise. Feathers fall slowly, and large rocks fall much faster than feathers or hot air balloons. Is this a falsification of Newtonian mechanics? No, because we just adjust our conceptual framework to include an atmosphere and density. If you throw the object sideways, absent aerodynamic lift provided by the air, it should not fall any faster or slower, but in fact if you throw it fast enough, it will never come down again. That is to say, it will have entered into orbit. Well, okay, we adjust our conceptual framework again. The Earth is a sphere, so throwing an object sideways is actually imparting a tangential velocity, and you can think of the object as always falling and always missing, and so Newton's law of gravitation hasn't been falsified. But aha! If something is moving relative to us, its apparent mass and size is different and time behaves in wonky ways, in clear and unambiguous violation of Newton's laws of mechanics. Surely we can't save them this time with a change of conceptual framework, can we? Well, not all the time, perhaps. But it turns out that Newton's and Einstein's laws of motion produce very similar answers for relatively small things, moving at speeds that we're used to. In fact, for most things we encounter in this world, we can't measure their motion accurately enough to tell the difference between the two laws of motion. So we can save Newtonian mechanics in ordinary life by changing our conceptual framework from wanting to know what's true to wanting to know what's at least fairly close to true. By taking off our scientist hats and putting on our engineer hats, we can keep talking about how Newton's laws of motion are true, and teach them in high schools as if they are true, and so on. And to extrapolate this one step further, to show you just how significant the Quine-Duhem thesis is, if it eventually turned out that Newton's laws don't even come close to applying to bright yellow racquetballs, that bright yellow racquetballs, despite having the same mass and density as their blue counterparts, fall up, not down, and speed up with friction but eventually slow down in a vacuum, we would still not abandon Newton's laws of motion. Physicists would get very excited and go write some very complicated equations, which no one would use in practice, and we'd all just stick with blue racquetballs and note that it turns out that there are now two places we shouldn't apply Newton's laws of motion, and move on with our lives. In fact, and this is almost a law of human psychology, it is nearly impossible to prove to someone that they should stop using something which they have found useful. And we can see this in the irony that, despite the event that inspired Popper to create falsificationism having actually falsified Newtonian mechanics, all it did in practice was verify relativity. This is also, perhaps, why it has been said that scientific theories which are false tend to be abandoned one funeral at a time. So while kids' shows like Dinosaur Train will keep saying things like, a hypothesis is an idea you can test, don't forget to teach the kids who watch them, when they're old enough to understand. That's more an ideal than reality. I'm going to give the last word to Eve, who actually gave her last word to the eminent philosopher of science, Paul Feyerabend. Knowledge so conceived is an ocean of alternatives channeled and subdivided by an ocean of standards. Today this view is often connected with the name of Karl Popper. Popper's standards of comparison are rigid and fixed. Popper's standards eliminate competitors once and for all. Theories that are either not falsifiable or falsifiable and falsified have no place in science. Popper's criteria are clear, unambiguous, precisely formulated. This would be an advantage if science itself were clear, unambiguous, and precisely formulated. Fortunately, it is not. To start with, no new and revolutionary scientific theory is ever formulated in a manner that permits us to say under what circumstances we must regard it as endangered. Many revolutionary theories are unfalsifiable. Falsifiable versions do exist, but they are hardly ever in agreement with accepted basic statements. Every moderately interesting theory is falsified. Moreover, theories have formal flaws, many of them contain contradictions, ad hoc adjustments, and so on and so forth. Applied resolutely, Popperian criteria would eliminate science without replacing it by anything comparable. They are useless as an aid to science. Until next time, May you hit everything you aim at.